Hello, Calculus. This is Mrs. Bricky and lesson 1.3, talking about infinite limits and limits at infinity. So thinking back to last year, we graphed rational functions. And rational functions, when we're looking at their graphs, we often want to see the function in factored form, which may mean that you had to factor it, but this one's already factored for us. So we want to think about the graph of this function right here for just a minute, and then we'll talk about how limits apply and what this means for what we're talking about in calculus today. So you might recognize right away that there's a factor of x minus 1 in the numerator and a factor of x minus 1 in the denominator, and that means this function would have a hole at x equals 1. At the other two factors in the denominator, we would have a vertical asymptote. So we can't divide by 0, so any factor in the denominator that doesn't reduce is going to cause a vertical asymptote in the graph. Well, the first factor, x minus 2, that's going to cause a vertical asymptote, it has a power of 2. So we would call that an even vertical asymptote at x equals 2. And again, it's even because of that power. 2 is even. And then it would have an odd vertical asymptote at x equals 4, that other factor. And the reason we will call that an odd vertical asymptote is because the power, 3, is odd. So if you look at these graphs below, what it means for an asymptote to be even or odd tells you whether or not the two sides agree. So for an even vertical asymptote, the two sides will either both go to positive infinity or both go to negative infinity. For an odd vertical asymptote, the two sides will have opposing behavior, either going up on the right and down on the left, or vice versa. So we're going to kind of look at how this connects to limits. We've already been writing some limits. So on this one, we would say the limit, I'm going to call this c, as x approaches c of the function goes to positive infinity. For this one, we would say the limit as x approaches c of the function, it goes to negative infinity. And these two limits, we would just have to say do not exist. Or if we looked at a one-sided limit, we could say what is happening. So when we talk about infinite limits, this is what we're talking about. We're talking about the function is increasing to positive infinity, or the function is decreasing to positive or to negative infinity. So if possible, instead of does not exist, we do probably prefer to give that positive infinity or negative infinity, unless we're not able to. Now, to do infinite limits, we oftentimes have to do what's called a sign analysis. And so we're going to use our knowledge of even and odd vertical asymptotes as well as holes and a little bit of sign analysis to help us figure out these limits right here. So the first one is the limit as x approaches 2 from the right side. Always you want to check direct substitution. If we substitute into, for this equation, 2 plus 3 would give us 5 on top and 0 on the bottom. So we can't use direct substitution because 5 divided by 0 is undefined. So instead, we're going to do a sign analysis. Sign analysis means we're just going to think about whether the numerator and denominator are going to be positive or negative. So if I substitute a number just to the right of 2, like maybe 2.01 or something, doesn't matter the particular number, just think of a number just to the right of 2. If we sub that in, that's going to be a number a little bit bigger than 2 plus 3. That's going to be positive. And we don't have to think about the exact number. We just have to think about its sign. In the denominator, if we sub in a number that is just bigger than 2, we're going to take that number that's just bigger than 2 and subtract 2, and that's still going to be positive. It's not going to be a very big number, but it's going to be a positive number. So positive over positive means that this is going to be approaching positive infinity. For the next example, we're going to approach 2. So it's exactly the same function. We're approaching 2 from the left side. So again, we're going to think about that sign analysis. If I put in a number just to the left of 2, so a number like maybe 1.99, my numerator is going to be, a number a little bit less than 5. So that's definitely going to be a positive number. In the denominator, if I put a number that's just less than 2, and I subtract 2 from it, that's going to give me a negative number. And again, if it helps you, you can think about a particular number like 1.9 or something. So in this case, because we have a positive divided by a negative, that means that the limit is going to be negative infinity. So we looked at it from the right and from the left. For this function, this is an odd vertical asymptote. So it makes sense that we saw that one side is going to positive infinity and one side is going to negative infinity. So here's another function, x minus 2 over x minus 1 squared, and we want to take the limit as x approaches 1 from the right, and then in number 4 from the left. So again, if we tried direct substitution here, we would get negative 1 over 0, and that is undefined. So direct substitution doesn't work. So we're going to do a sign analysis instead. So if I think about subbing in a number that is just to the right of 1, so like maybe 1.1, the top would take on the sign of negative because I'm subtracting 2 from a number that's close to 1. In the bottom, it kind of doesn't matter what number I'm subbing in there, right? Because whatever I do right here, I'm going to square it. So the denominator is automatically going to be positive. Whoops, I don't mean to cross that out. Because it's squared, it's always positive on the bottom. So our sign analysis tells us that we're going to have a limit of negative infinity. I wish number 3 and 4 were on the same line. They're the same function. So this is the same function, but we're approaching it from the left. So on this one, again, direct substitution is the same as before, so it doesn't work. So if we think about our sign analysis in the numerator, we're subbing in a number that's just to the left of 1. So if you want to imagine like 0.9. So the top will still be negative, just like it was before. And again, the bottom is always positive because it's a number squared. And when we square a number, it always becomes positive. So again, this is negative divided by positive as far as the signs go. So we would say this limit approaches negative infinity. Thinking about your skills from last year, we know that this thing has a vertical asymptote at x equals 1. It has an even power, so we should find that it's an even vertical asymptote. And when we checked the two sides, we checked the right side, we checked the left side, and they are both going to negative infinity. That's an even vertical asymptote. So it looks like this at x equals 1. They're both going downward. Okay. All right, we've got one last one. Now, just because you see a number in the denominator does not mean that it's going to be a positive infinity or a negative infinity. So always start with direct substitution. Direct substitution here leads to 0 over 0, which is undefined. So we have to use another strategy. This one is factorable on top. So we're taking the limit as x approaches 2 of x plus 2 times x minus 2 over x minus 2. That can be reduced. This is the same as the limit as x approaches 2. If we reduce that, it will just be an x plus 2. So you can see that that limit now we can do direct substitution to get a limit of 4. So this is not a vertical asymptote at all. We have a hole in the graph, and that hole is located at 2, 4. Okay, now we're going to talk about limits at infinity, which is much different. So infinite limits are vertical asymptotes. Limits at infinity actually have to do with the horizontal asymptotes that a graph might have. So if the graph of a function approaches a horizontal asymptote on the left and or the right side, it's said to have a limit at infinity. So I have kind of a little graph example right here. This is a rational function. It has some end behavior here on the left-hand side and the right-hand side. It's approaching 1/2. If you look at the scale there, that's 1/2. The red makes it look like a negative 1/2. Anyway, so if it has that horizontal asymptote, then we would say that the limit as x approaches infinity of that function is the value of that horizontal asymptote. So limits at infinity are involving the end behaviors of the graph of the function. You might recall from pre-calculus or from last year that when we're thinking about end behaviors, when we're thinking about the far right hand and the far left side of the graph, we only need to really consider the highest degree term in the numerator and denominator to try to decide what's happening, because all of the other terms are so much smaller that those leading terms are really just controlling the behavior of the function on those far sides. All right, so we're going to look at some pre-calculus examples and connect them to the limits. So, last year I might have given you this function and asked you to find the horizontal asymptotes, and you would look at the leading term in the numerator and the leading term in the denominator, and you'd compare their powers. So for a function that had the same power for the leading terms, then the horizontal asymptote would be at the ratio of the leading coefficients. 5/10 is the same as 1/2. And I'm going to jump down to 9 now because this is the same function written in limit notation. So if we're looking for the limit as x approaches infinity, we're again just considering those two largest terms. They have the same magnitude. They're both power 4. So we would say we just need to consider their coefficients, and we would say that this limit is equal to 1/2, just like finding the horizontal asymptotes of a rational function. This actually happens to be the function that I showed you the graph for right here. So on each side, both the right and the left, it's approaching 1/2. All right, so for the next, let's look for the other two kind of scenarios. This was if the powers are the same. If the powers are the same, the limit is the ratio of the leading coefficients. All right, so now we've got one where if we look at their leading terms, the top leading term and the bottom leading term, they are a different power, and I have a higher power in the denominator. If you have a higher power in the denominator, that denominator is going to be a much bigger number. So if I have a smaller number and I'm dividing it by a much bigger number, that's going to give us 0. So the limit as x approaches negative infinity for this, and it would be the same on the left and the right. So whether it was a positive infinity or negative infinity, we would get that answer of 0 for the limit. So anytime you've got that higher power in the denominator, the limit as x approaches positive or negative infinity will be 0. Okay, so the last possibility would be that when we compare their leading terms, we have a higher power in the numerator. So in that case, we would say that there is not a horizontal asymptote. You might remember, and you might not remember, it's okay, that this would be a slant asymptote. And we would typically use long division to figure out the equation of that slant asymptote if we needed it. We don't need it. We would just say, if we were talking about limits, we would say that the limit does not exist. Again, that's because we've got this much larger number divided by a much smaller number. And so you could also maybe give a little bit more information here because these are both positive leading terms. This would approach positive infinity. If we looked at a graph of this, it would, do who knows what in the middle, but then it would be like going off towards some higher value there. Okay, so those ones were all in standard form. If you have to take the limit at infinity of a function that is in factored form, you still want to try to compare those highest degree terms. You don't need to multiply them out, though. You can just be smart about thinking about what the leading terms would be. So this is the limit as x approaches infinity. And if I think about what that leading term is for the numerator, I've got a 2x and I have an x minus 1 squared. Well, if I square x minus 1, its leading term is going to be an x squared, and we're multiplying that by a 2x. So the leading term here is going to be 2x to the third. And I don't really care what the other terms are because the 2x to the third is by far the most powerful term, and it is really controlling the far right and far left behavior of that graph. In the denominator, I have a factor of x plus 2 and a factor of 3x minus 1 squared. Well, the 3x minus 1 squared is going to have a leading term of 9x squared, but then we're also multiplying that by this leading x. So that would give me a 9x to the third as my leading term. And again, I don't even care what the other terms are. So now I can apply the same kind of rules that I applied before. Since the two powers of these leading terms are the same, our limit is going to be the ratio of the leading coefficients, and that is going to be 2/9. Okay, so for rational functions, they have at most one horizontal asymptote, and the limit is the same whether x is approaching positive infinity or negative infinity. But in calculus, we get to deal with some kind of cooler functions that are more interesting. And one type, radical functions, they frequently have two different horizontal asymptotes, one on the right and one on the left. And I'll show you a graph in just a second, but I want to find the limits first because the graph will obviously give it away. So when we're doing this sort of limit with a root like this, the square root of 4x squared minus 3, it still is the leading term that controls the behavior of the function. That little minus 3 there, it affects what's happening kind of in the middle of the graph when we're at those lower x values. But once we get out onto the far left and the far right of the graph, that minus 3 basically does nothing. So if we think about this 4x squared being under a square root, this is so fun, that's going to basically be the same as the absolute value of 2x. So you can probably see where the 2 came from. The 2 came from square root 4. And you can probably see where the x came from. The x came from square rooting an x squared. That square root needs to be positive though, and so that's why we throw those absolute value bars around it, is we know that when we take the square root like this, that we end up with a positive result. So we put absolute value bars around the 2x. So our numerator ends up being absolute value of 2x. Our denominator is just x. So for this function, square root of 4x squared minus 3 all over x, its limit is going to be exactly the same as the limit as x approaches infinity of the absolute value of 2x over x. And as we're approaching positive infinity, this numerator is going to be a positive number no matter what. The denominator is also going to be a positive number, but the numerator is twice as big. So this limit is 2. And it's definitely a positive 2 there. So we have exactly the same function here. We just want to think about the limit as x approaches negative infinity this time. And again, the square root of 4x squared for large or small values of x is going to be about the same as the absolute value of 2x. But this time, if we think about like a sign analysis, if I sub in a very, very large number on the top, a very large negative number, I guess, on the top, I'm still going to get a positive number out of that. So my sign analysis tells me that the top is going to give me a positive value, but the bottom, when I sub in that negative, really big number, is going to be negative. So this one is going to actually approach negative 2 on that left side as x approaches negative infinity. So I want to show you the graph because the graph is kind of cool. Here it is. So you can see it's doing exactly what our analysis told us. On the far right side, its asymptote is at 2, and on the far left, its asymptote is at negative 2. So it has these two separate asymptotes. It actually has this giant gap in its domain as well, and that's for values of x, for which that square root would be the square root of a negative number. So they would be non-real, and they don't show up on the graph. They're not part of the domain of that function in the real number system. All right, rational graphs, those are fun. Okay, so the last thing we're going to do is think about some limits that involve exponentials, particularly e to the x. So thinking about the graph of e to the x, which you're totes familiar with, if we think about maybe subbing in some values here. If we sub in 0, well, e to the 0 is 1, so it has a y-intercept of 1. And e to the 1 would be e, which is 2.7, and it just grows faster and faster and faster. And then over on the right side of the graph for an exponential, you probably remember that it has a horizontal asymptote at 0. So y equals e to the x looks something like this. So we're going to use the end behavior of e to the x to help us decide about these limits above. The first two are straightforward. Just what is the left-hand limit? What is the limit as x approaches negative infinity of this function? And you can see that that is 0. It's that horizontal asymptote on the left. This one is the limit as x approaches infinity. So we're looking at the right-hand side of this function, and you can see that that is approaching infinity. It's just growing. Also could say does not exist. But the way that it does not exist is that it's approaching positive infinity. Okay, so let's see how we can apply that to some more complicated limits. So we want to take the limit as x approaches infinity of e to the negative x plus 2x squared minus x over x squared plus 3. So when we're taking a limit like this, we can think of the limit of those two terms individually. So we can think of this limit and this limit individually and then add those two limits together. So that first term, so we want to think about the limit as x approaches infinity. And I'm going to rewrite this so that it doesn't have that negative exponent. E to the negative x is the same as 1 over e to the x. And then that second limit, so I'm going to separate it. just to help me think about it a little bit better. That's the limit as x approaches infinity of 2x squared minus x over x squared plus 3. Okay, so let's do those one by one. E to the x, if you can almost think about this as direct substitution. Think about subbing a big number into this. This is going to be 1 divided by a huge number, because e to a big number is just an even bigger number. So if I have 1 over some huge number, that limit as x gets bigger and bigger and bigger, that's just going to get closer and closer to 0. 1 divided by a big number is going to get closer and closer to 0. The second limit is a rational function like we've been working with before. So I compare those leading terms. They both are power 2. So I look at the ratio of their leading coefficients. That's a 2 over 1. So this limit is 2. So I can say the limit of this function up here as it goes to infinity is going to be 0 plus 2, which is 2. Okay, the last one. Technically not a rational function because of that e to the x, but we can still just consider the most powerful term in the top and the most powerful term in the bottom in order to figure out our limit. So in the top, the most powerful term is a 2x squared, and in the bottom, comparing an exponential term to a quadratic term like this, exponentials really do grow a lot faster than quadratics, even with a coefficient of 3. So exponential definitely is going to be the larger term there. So now what we have to think about is which of these terms is going to grow faster, which one is going to, get big sooner. And that's kind of a weird question to think about because, if we put a large number in here, this top is going to be a big number, but the exponential is so much bigger that it's going to actually approach 0 because the bottom wins. It's going to be like a small number over a bigger number. And even though this one is getting bigger as well, this one is getting bigger so much faster. I mean, think about if you were doing like 1 over 10 and then 2 over 30 and then maybe like 3 over 90. This is growing, but this is growing so much faster that these fractions are just approaching 0. Now, if it had been flip-flopped, if we had been doing the limit as x approaches positive infinity of e to the x over 2x squared, then that would approach infinity because the top is so much bigger than the bottom. So that would just get bigger and bigger and bigger. These ones are a little tricky and we'll keep practicing them, so don't worry about it if you're like, huh? Because we will practice them and we'll talk more about how you can tell, which function's going to kind of win. So, if the top wins, getting bigger than the limit would be positive or negative infinity, depending on the signs. But if the bottom is winning that contest of growth, then the limit would approach 0. Okay, here is your assignment. Again, if there's any that you're struggling on, just keep track of those ones. And when I'm back at school, we will revisit those and talk about them. Thanks so much.